Okay, this morning I'm going to talk about something called the Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium takes into account this thing called genetic equilibrium. And you can see the definition there at number 1. If a population is not evolving, the allele frequencies in its gene pool do not change. So what's that mean? Basically, it says that stuff remains constant from generation to generation. So we have these alleles, remember, different forms of a gene. If a population is not evolving, those stay the same from generation to generation, no matter what. This is a hypothetical because in the real world, populations change. Populations are subject to genetic drift, which is covered in previous videos. Populations are subject to mutations and natural selection. Okay, so that takes us to this thing called the Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium states that, in just the definition written right here, allele frequencies in a population should remain constant unless one or more factors causes those frequencies to change. Okay, so in the real world, we know that things are going to change. Hardy-Weinberg equilibrium is a way to mathematically represent those changes from generation to generation, and we're able to see if a population is evolving. Okay, again, let me state that in the real world, every population is subject to change. It's just that some are going to change a little more easily than others. So you see the equation here for the Hardy-Weinberg equilibrium. P squared plus 2pq plus q squared equals 1. So what the heck does that mean? Well, P and Q are going to represent our dominant and recessive alleles. Okay, so P squared would be 2 dominant alleles, right? So big A, big A. 2pq would be our heterozygous, big A, little a. Q squared would be little a, little a. All right. So if I take these numbers, plug them into my formula, they should equal 100%. So I do this for one generation, and then I check the next generation. If it's still the same, then the population is not changing. Okay. So you have this equation here. So frequency of homozygous genotype, homozygous dominant, plus frequency of heterozygous, plus frequency of the recessive genotype. So I have a little sample problem. Oops. Okay. Sample problem. Suppose that one generation's frequency of allele A, the dominant allele, is 40%, and the frequency of allele lowercase a is 60%. So I plug them into my formula here. Genotype AA would be 16%. How did I get that? Well, I take capital A, square it. So it's 0.40 squared gives me 16%. Do the same thing with the lowercase a. So Q squared, so 60% squared, 0.60 squared equals 0.36 or 36%. And then lastly, the probability of big A, little a is 2 times 0.4 times 0.6. That gives me 48%. So if I have these predicted allele frequencies in the next generation, then no evolution is happening. However, if these frequencies change, if it goes from 16% to 13%, or 36% to 39%, or whatever it may be, then I know that something is taking place and is allowing allowing evolution to occur within this population. It's a complex concept. There are worksheets for you to do in your packet. Highly suggest that you do them, calculating allele frequencies, and then some things about Hardy-Weinberg equilibrium. Take a stab at those, see how it goes, and then we'll have some time for questions when we come back together.